Oh, hey guys. Question. How are programming languages converted to machine code? In our exploration of software programs, we discussed the high-level aspects of a programming language. To summarize, the language that a computer understands, machine code, cannot easily be read by humans. So we use programming languages that we can read and write, and then convert that to machine code. But what does that conversion process look like? How does it work? Let's start by discussing the two main concepts that we can use to take source code we write and convert it to something that can be executed by a computer. These are compilers and interpreters. What's the difference between the two? Compilers take the entire source code of a software program and convert it to an artifact. Usually this artifact is machine code. This machine code can then be distributed and executed on a computer. Compilers that produce machine code will produce it for a specific processor architecture, meaning that we'll need to compile our program for each architecture we'd like to support. Once compiled, we no longer need the source code of the program. If someone wants to execute our program, we can give them the compiled machine code, the binary, and they can execute that without ever needing access to the source code. Technically, if we wanted, we could throw away the source code after compilation. The proposed advantage to compilers is that because the conversion from source code to executable happens before the program is ever distributed or executed, any analysis and optimization of the underlying machine code instructions has already been performed by the time the program is executed. The compilation process takes time and tends to make the program more efficient. The proposed disadvantage to compilers comes from their advantage. They require the compilation process to be performed before the program can be executed. If any change is made to the source code, a slow compilation step must be performed before executing the new version of the program. On small programs, this slow compilation step seems negligible. However, as the program grows in size, so does the compilation time. What about interpreters? Interpreters are programs themselves. At the most basic level, they read each line of the source code of a program as it's being executed, convert it into machine instructions, and then execute those instructions. Because interpreters process the source code of a program at runtime, we always require the source code to execute the program. So unlike compilers, we could not throw away the source code if we wanted to. A proposed advantage of interpreters is that they don't require the slow compilation step that the compiler approach requires. This helps speed up development time. However, because the interpreter is in charge of converting the source code to machine code, the interpreter program itself needs to be able to support the processor architecture we want our program to run on. If it doesn't, then we may be in trouble. A proposed disadvantage to interpreters is that due to them, at a basic level, processing and executing a program statement by statement, they generally don't execute as fast as compiled programs. So which is better, compilers or interpreters? Well, it depends on our situation. If we are writing a program where speed matters, or if we simply don't want the computers using our program to have an interpreter installed on them as a prerequisite to running our own program, then leveraging compilation may make sense. In many cases, speed actually doesn't matter that much. If we're just writing some helper programs, or a basic application, interpreted programs still run more than fast enough for our needs. The reality for the majority of software engineering use cases is that we use the approach that ourselves and our team are experienced with, unless we have a very good reason not to. We've spoken a lot about compilers and interpreters, but which programming languages are interpreted and which are compiled? Well, all programming languages are just specifications. They define a set of words and symbols, and what should happen when those words and symbols are put together in specific ways. An implementation of this programming language specification can then be created, and the implementation of the programming language may then be compiled, or it may leverage an interpreter. Take the programming language Go as an example. The Go language is merely a specification describing how the language should function. I've linked the specification in the description. The implementation of Go that most engineers would be familiar with is compiled. However, there have been Go interpreters created to allow Go source code to be executed in an interpreted manner. To make things simple, most languages have a common implementation that most software engineers would be familiar with. The most common implementation of PHP is interpreted, and the most common implementation of C is compiled. What about Python? The most common implementation of Python has two steps. The first is a compilation step, from the source code to an intermediate language called bytecode. This bytecode, unlike machine code, is not specific to a processor architecture. It's still abstract. The second step is an interpretation step of the bytecode while the program is being executed. So some programming language implementations have a hybrid model of compilation and interpretation. In summary, we use compilers and interpreters to convert the source code that we write into something that can be executed on a computer. Compilers generally produce more efficient programs at the cost of a slow compilation time. Interpreters have zero upfront compilation time at the cost of a slower execution time. Are there any other approaches to converting source code into an executable program? Is there a middle ground? Well, there is. It's called just-in-time compilation, and we'll discuss it in a future video. Thanks for watching, guys. I'll see you next time.